Hello, this is Chuck Ridgway, Automation Technology Manager at Horner. Thanks for joining us for another Tuesday live stream. Well, it's September already, and that means summer is just about over. We're heading into fall, and our first topic as we head into fall is more little known but useful system registers. So back in the summer, I think it was in July, we first covered useful system registers. And as I was doing research for that particular topic, I realized there were a bunch of useful system registers for application designers. So I figured we'd probably be revisiting this topic again. And here we are for the second time on system registers. And I've got 3 new system registers for you to learn about today. Okay. So before we dive into today's topic, though, let's bring in our product manager, Mr. Casey Gardner. How are we doing, Casey?
Hey, not too bad. How's it going, Chuck?
Going great. So this summer, one of the things we did get accomplished is we've started the process of the Cscape beta program. So how do you think the Cscape 10 beta program is going?
It's been going good. As always, we're encouraged to get feedback from customers and help fine tune it to everyone's best experience. So been collecting a lot of that feedback and ultimately going to make the product better for it.
You bet. And I'm looking forward to kind of the second release of the beta code for Cscape 10 because we've already incorporated some of the improvements that have been requested by the testers. All right. Now I've got a hard-hitting question for you here for this one. Besides, wrapping up the Cscape 10 beta program, what are you looking forward to in the fall?
Well, we've got a football luckily starting up this week, and again, you with your Lions and me with our Chargers fan first and foremost. So we're definitely looking forward to this week and the rest of the fall and winter for sure.
Absolutely. So if you couldn't tell already, Casey and I are big football fans. And even though we both live in the Indianapolis area, it just so happens neither one of us are necessarily Colts fans. I mean, we don't root against them unless they're playing our team, of course. But we just happen to be, a Chargers fan out there with Casey. And then I'm a Lions fan. So I think I've mentioned that before. That's my, my legacy logo hat that, from when I was a kid. And of course, being a Lions or a Chargers fan, it's been pretty tough sledding, frankly. But both of us are optimistic this is going to be the year. So we'll see what happens as the season goes. And my particular case of maybe falling from the optimism train may happen earlier because I'm heading out to Kansas City to watch my team play the World Champion Chiefs. So that's going to be a tough one. All right.
Yeah, Week 1's always a good reality check. We'll see.
Absolutely. Well, while I'm actually covering an automation topic today, Casey's going to be standing by answering any questions you have in the chat section. And for those of you watching on replay, like a lot of you do, give us your comments in the comment section. We'd love to see those, and we'll react to those just as soon as we can. All right, let's dive into today's topic and see how we're going to break it down. All right, so we're going to do a quick review of system registers. What are they and what makes them so useful? And then as I mentioned earlier, we've got 3 overlooked system registers that we're going to cover in today's program. And for each of those, we've got application examples and we'll have demonstrations throughout. All right, here we go. Okay, so what are system registers? Well, system registers are one of the built-in type of memory registers available in every Horner OCS. And these typically deal with either system status or system settings in the unit. And a good way of thinking about system bits and system registers is the fact that just about every parameter that you'll find in the system menu on a Horner OCS typically has an equivalent system register that corresponds to it. Now, system registers are sometimes read-only, sometimes read-write. It really depends on the function of the particular system register. Now we've got 2 different types of system registers, bit type, and there's only about 13 of those. Those are type S. And then the most prevalent type are the system registers, or type SR, and there's at least 192 of those. And with some units and with some logic languages, there's even more. Now, because there's some variation from unit to unit and even from language to language, I highly recommend that before you start a project, you check out the user's manual for your particular OCS unit to check out the chapter on system registers so you can see specifically which ones are available for you to utilize in your project. Now, as I mentioned, back in July, we had our first visit to this topic, and we covered 3 specific system registers. We covered using a system menu shortcut. We talked about taking advantage of the unique OCS serial number that's built into every controller that we manufacture. And we talked about the fact that you can access the system coordinates for the last touched area on the screen by monitoring system registers. And for all 3 of those things, we talked about applications where you could use them and how to use them. So go check that out if you can. So now let's dive into those 3 specific system registers that are often overlooked that we're going to tell you how to take advantage of today. All right, we're going to start with a relatively simple one, and that is the system beeper. So what many of you may not realize is that the beep that you hear when you press the touch screen, which can be enabled and is by default, or disabled, that beeper can actually be triggered from logic or from the screen using system registers. So specifically, it's SR184 that's used, and it's really only the lower bit. And if that lower bit is a 1, the beeper's on, and if it's off, the beeper's off. Now, why would you want to trigger the beeper separately? Well, it can be useful for a variety of different functions. So for example, maybe you want to get the operator's attention when a new alarm condition occurs, and the operator is, checking out what's going on in the machine and not necessarily looking at the touchscreen all the time. So you could beep the beeper and get their attention so they can check out the screen and see specifically what's happening. Also, maybe the operator is manually trying to load a part in some sort of fixture, and sometimes it can be a little tricky to tell if the part is fully loaded or fully nested, for instance. Well, of course, if you've got a sensor built into your fixture there, you could enunciate using a beep, just a simple little beep, to tell the operator, yep, that part's nested just fine. So there's a couple of examples of how you might utilize the beeper in the process of your application. All right, so let's take a look at an example here on the screen, and let's start out on the bench. So what I've got going here on the bench is I have, let's go to the beeper screen here. So I've got a demonstration here on how I might utilize the beeper. So one thing I did just real simple was I connected a push button on the screen that will trigger the beeper. So let's see how that works. So the longer I hold in that bit, the longer the beeper is on, which means we can maybe have a short beep to do one function and a long beep to do another. We could even do patterns of beeps if we wanted to. But in this example, what I'm going to do is I'm going to use that kind of part nesting example of providing validation to the operator that a part is nested and they can continue. So when the limit switch turns on that indicates the part is nested, we're going to give a short beep. So you can tell whenever that switch turns on, I'm turning that beeper on, say for 50 milliseconds or so. And then also, if we have an alarm condition, I'm going to go ahead and execute a long beep. Okay, so we've got the long beep. The idea is for the operator to check out the screen and see that, yep, we've got a motor load condition. Okay, or maybe we've got a part jammed or something. Okay, so there's a couple of examples of how you can utilize the system beeper through system registers to maybe call attention to some conditions on a machine to the operator. So how were we able to make this happen on the Cscape side? Well, the first thing we did was we had to map that beeper system register right there, SR184. We needed to map that over to a variable. Now I'm using variable base advanced ladder like I often do. Okay, so I created a variable called beeper, which is Boolean, and I mapped that over to the only bit in SR184 that matters. That's the lower bit, SR184.1. So every time my beeper variable turns on, SR184.1 turns on. All right, and how did I use it in my program? Well, I created a coil called beeper, all right? And then I have 3 different ways I can turn that beeper on, which effectively turns on SR184.1. I've got a long beep, I've got a short beep, and I've got a beeper test from just that push button on my touchscreen. Okay, so you could do the rest of this logic any way you choose, but basically what I did is I said, okay, if I have an alarm condition, I'm going to detect I have a new alarm condition, and I want to turn on the long beep variable, and then the long beep variable will be on for about a second, and then I'll turn it back off again. All right, so that's the long beep that I am going to have occur whenever I have an alarm condition. And then I also programmed in a short beep, so when my part became nested, I initiated a short beep that lasts for 50 milliseconds or so. And of course, when that turns on, my short beep contact here turns my beeper on. Okay, so that's what I did. The key point here, of course, is mapping SR 184.1 over to my own variable in my program. All right, one more thing I want to show you in regards to the beeper, and that is in my application, I wanted to turn off the normal beeper, the beeping that happens whenever I press the touchscreen. I wanted to disable that so that the only beeping coming out of my unit would be, something that I wanted to alert the operator to. So I also mapped a variable to SR 183.1, and that is a system register that when it's on, causes a beep to happen on every key press on the touchscreen, and when it's off, it prevents a beep from happening on every press of the touchscreen. So I put some logic in with an always off contact, making sure that SR 183.1 through this variable is always off. That way, when the operator hears a beep, he knows it's either an alarm condition or his part is nested or something intentional like that, and not that just somebody standing behind him had pressed a button on the screen. All right, so let's continue on with our second overlooked system register, and that is the ability to make clones or load clones. So for those of you who aren't familiar with cloning in the OCS, the make clone feature is the ability to save away the program in the OCS along with all the system settings, along with all the variable values, okay? And that can be saved away to micro SD, and it effectively is stored in two files, okay? One with the program in it and one with all the rest of the settings in it. So why would you ever want to do that? Why would you ever want to trigger that, maybe from logic or differently on the screen than what you can access through the system menu? Well, maybe you've got a machine that goes through several changes in terms of parameter setups and those sorts of things, and you would like to have a clone of that stored away on micro SD, so that if you ever have a scenario maybe in which you need to replace the controller or you have some other issue, you can quickly recover and get back to where you were with a fully set up and operating machine. So that might be one reason you'd want to make a clone. Well, making a clone from the system menu might be a little dangerous to allow operators or even some, inexperienced maintenance personnel loose on the system menu. So by creating maybe some more user-friendly screens in the application, or by maybe triggering the making of the clone directly in logic, you can take some of the potential risk away from making the clone. Okay, so that's one application where you might really want to accomplish that. Now, how can we actually make the clone by manipulating the system registers? Let's talk about that next. Okay, so effectively, we've got 4 different bits that we can either manipulate or monitor. So let's start with the make clone bit, which is SR 164.9. When we turn that bit on, okay, then effectively it initiates the make clone process. And then as soon as that process starts, whatever screen the operator was looking at, the screen will quickly change to the clone screen in the system menu, okay? And then when the clone is complete, then that bit that we set is cleared, and then the screen returns back to the previously displayed screen. And then we can also monitor another bit, SR 164.11, which will tell us if there's a problem. And if there is a problem, we'll know that the clone did not execute completely. And the reason it probably didn't, most likely, is probably because there wasn't a memory card installed in the unit or somebody had pulled it out. Okay, so that's the process you would make for making a clone. Now, some people, when they're creating user-friendly screens to trigger someone to make a clone, they may instead maybe want to call it backing up the machine or something like that. All right, now to go the reverse direction, to restore or to load a clone, okay, how would you do that? Well, it's basically just by turning on and leaving on a different system bit, SR 164.10. And then when that bit is turned on, the load clone is initiated. In other words, the program is loaded from the memory card. And then because this is part of the normal make clone process, as soon as that program loads, the unit reboots. And then after it's done rebooting, of course, the OCS will be displaying whatever the initial screen is. Okay, so that's what's happening with the process of loading a clone. Okay, now let's go back to the bench and take a look at effectively executing this with my demo program here. Okay, so let's head to our next screen. And what I've done here is, I've just created some buttons here on the screen to show how this could work. And I've labeled the make clone button actually backup machine. Okay, so this bit is actually tied directly to that specific system register bit, which initiates the make clone. Okay, and then this is an indicator that I have the ability to reset from the screen that tells me if that backup fails. So let's see if we can initiate a makeup clone, which we're calling backup machine here. Okay, so I'm going to pull the memory card first so that when I back up the machine, after briefly going to the system menu, it immediately failed. The backup immediately failed. And that's, of course, because we don't have a memory card in. So I'm going to clear that error here, correct the issue by plugging in the memory card. And then this time, when I press backup machine, all right, we go to the clone screen. The make clone is executing. And then when it's done, we go back to the screen we were on before. And because the failed bit is not on, we know that everything is good. And then similarly, if we want to restore the machine from a memory backup, we could do that from the screen here as well. So this restore bit is tied directly to that load clone system register bit. So again, if I pull the memory card, all right, and press restore machine, I immediately fail. Now, of course, I could clear that error if I choose to, or I can just correct the issue by plugging in the memory card and try again. And this time, we load the new program from the memory card, and then almost immediately, as soon as that is done, we go through the rebooting process. Okay, so that's just the normal part of the load clone, and that is load the new program, then reboot to load all the system settings and all the system variable values, and all the variable values for that matter. Okay, so, and then of course we end up on the initial screen for the OCS, not necessarily back to where we were before. Now, everything I showed you in that demo didn't really require any logic at all. It really just required me mapping variables for, push buttons and indicators that are on the screen to the specific system registers that we were talking about there for make clone and load clone, as well as the indicators that let you know when they fail. Okay, so there really wasn't any ladder required there at all. However, there is some ladder you could choose to add to your system if you wanted to automatically, let's say, make a clone at the end of every day, which is certainly something you could choose to do. That way, if you ever had to replace your controller, the worst case scenario is that you'd be picking up where you left off 24 hours ago. Okay, how would you configure that? Well, very simply, you'd simply utilize time of day type function block here. So the way I've configured it, every day at 23:59, I kick off a one shot. Now that one shot is not directly used to write to SR 164.9, for instance, but it does actually trigger indirectly SR 149 so that we set that make clone bit and then let the whole process work itself out or play itself out. And then the firmware itself will clear the make clone bit, just like we demonstrated. So if you chose to create a clone every night at 11:59, that's how you would do it. All right, now let's talk about our last one, and that is the free running timer. So what is a free running timer? Well, if you were watching our live stream that we had, a few months ago, we covered making an analog totalizer using OCS. And one of the techniques I displayed was utilizing the free running timer that's built into every timer that gets added to your program in Cscape. Well, on top of that, there's also a free running timer that exists in the system registers. So that happens to be SR 149 and 150, which is an unsigned double integer value that's counting up in 10th millisecond increments. All right, so it's continuously counting up. There's no way to reset it. So it's always counting between a value of 0 and, that large number you see on the screen there that begins with a 4. So whether that's 4 billion or whatever that number is, that's a big number. So again, it's continuously counting up. So you can utilize that continuously incrementing free running timer and a little bit of math to effectively time any 2 events in your program if you want to use it in that way. So let's take a look at how we might utilize that on the bench as well. Okay, so let me head to the free running timer screen. And here you can see that I'm displaying the value of that system register 149 here on the screen. So what we have is a unsigned double integer value that's just counting up, and it'll eventually find its way all the way north of 4 billion, and then it will roll over. And in this example, what I'm using it for is to effectively time the cycle of my machine. So of course I could have added my own timers and counters to my logic, but instead I chose to utilize the free running timer and a move command and a little bit of math to do the calculation instead. All right, so I have input number 8 connected here as my cycle. So I'm going to turn my cycle on and then off again, and you'll see a new reading come in for the new cycle calculation. So every time I complete a cycle, I'm utilizing the current value of the free running timer, subtracting off the value when I started, and then coming up with the result. Okay, so you can use this free running timer for a whole variety of different functions, both functions that are really short in duration and ones that are longer. Now, one thing I want to mention here, the free running timer is just like any other timer in that its value inside your logic program is going to be read and fixed at the top of the scan. So the whole time you're solving your logic, the free running timer is at a fixed value. The next time you get to the top of the scan, of course, it'll have incremented. So it's not faster or more accurate, for instance, than the high-speed counter functionality that's built into every OCS, because the high-speed counter functionality, of course, is not scan dependent. So it's actually got dedicated silicon that is measuring time differences between inputs, which is obviously going to have higher resolution and more accuracy than what we can do for a scan-dependent scenario like I've shown here. But still, the free running timer can be extremely useful. So what logic was required for the free running timer? Well, like everything else, we start out by mapping a variable to the appropriate system register, in this case, SR149 as an unsigned double integer, okay, because that's what we have there. And then for the demonstration I did where I basically was timing the machine cycle, all right, I have a variable called machine cycle that's tied directly to %I8, all right? So when that turns on, we're going to trigger a one-shot bit. When that turns off, we're going to trigger a different one-shot bit. Okay, so when we turn on, we store away the current value of the free running timer in a double integer variable. And then when our cycle input turns off, it means we're at the end of the cycle. So at that stage, as long as our free running timer value is larger than the value we stored away, it's just a simple subtraction to get our cycle time. Now, there is one other case we have to account for, and that is if by chance, while we were timing, our free running timer rolled over. Because in that scenario, the free running timer value when we're done with the cycle will not be greater than the one we stored away. So in that case, we have to do some slightly different math to find the difference between the maximum value and the value we stored away and add that to the current value of the free running timer. Okay, so the free running timer can be highly useful, not with a lot of logic required either. Okay, so that pretty much wraps up the 3 different system registers that I wanted to demonstrate for you today. And keep in mind, system registers, whether they're %S type or SR type, those are registers that basically represent the status of the OCS or they also can be used to be written to sometimes to affect the operation of the OCS or the setup of the OCS. And there are several of these. There's a couple hundred available in most OCS units, and a bunch of these can be pretty useful in a lot of different applications. The specific system registers, that support varies by model, so check out your user's manual for your specific model. And today, of course, we highlighted the beeper, making and loading clones, and also how we might utilize the free running timer. Okay, so this is where I remind you that we're here every Tuesday at 2 o'clock, whether we're fully live like today, or whether we are streaming live and standing by to answer your questions. And don't hesitate to give us your questions in the chat section when you're watching live, or in the comment section when you're watching on replay. Okay, still a little bit of time left to sign up for IEC training, which is coming up here in about 8 days. All right, so head to our website and sign up for that. That still has a couple of open slots available, but it is filling up. And then next week, we're going to be covering utilizing an IO-Link encoder from a company called Kubler. So if you remember, IO-Link has been supported in the OCS now for several months through our partnership with Banner. And Kubler is a manufacturer of encoders. And like some companies, they do manufacture an IO-Link version of that. So we're going to integrate that and tell you all about it. I'm really looking forward to next week's show. Okay, if you haven't done so already, don't hesitate to subscribe to our channel. It doesn't cost anything. And if you choose notifications when you subscribe, you'll be notified every time we go live or every time we post a new video. Okay, so until next week when we talk IO-Link encoders with Kubler, let's all get out there and do us some good.